So, shall we go on? Oh, where is it down here? So, yeah. This is the first chapter, so we are going to start with the basics of machine learning, and we're going to understand what are the components of machine learning and how we do really train a model in this chapter. So basically, there's mostly like the background theory part in this chapter, which is a quite long chapter, and then after that, we're ready to start with the neurons. Okay, so let's start with some sort of motivation, like every course. So you might, I'm pretty sure like there are lots of you here who have done some, or at least have seen some results of deep learning, but just you can collect a bunch of things that have been done by deep learning, and they have really impressed human beings. So like you can consider like this image classification machine that can do the classification better than human beings. Or, for example, you can consider AlphaZero, so the algorithm which does play chess and can beat any world champion in the matter of the day. Or things like ChatGPT, nowadays many people use. So these are all got developed after the birth of deep learning. And I'm pretty sure you can add things that even I do not know about that here. So it's pretty much every day, everywhere nowadays. So there are a few things that started human beings to just get into machine learning or deep learning in more details. And one of the first ones was this image classification. So one of the very first things we wanted to do was that we're going to get an image, and then we want the computer, to tell us what kind of image is that. So is it a dog, cat, a bird, anything like that. So this was somehow a kind of old topic, but people tried a lot doing it like 1990s or even earlier, but they couldn't do it. Yeah, they could do it for basic things, but it was always failing. And then somehow they came up with this idea that machines cannot be really trained. But 1998, Lecture1 proposed the limit, which was not at that point really computable, so people could not implement it with the computers back then. But the idea of backpropagation let us implement this. And then it was 2012 when we started here at U of T, the AlexNet was proposed. And this was a kind of deep neural network, which, in theory, everybody knew this, but nobody believed that it's going to work. This went on this ImageNet challenge, which we are going to see it in details in this course. And at that point, this, for the first time, one neural network won the challenge. This was pretty much the birth of deep learning, and for this particular application of image recognition, this somehow got developed over and over. We had the DGG, then the ResNet came over, and nowadays we have crazy architectures, which for image classification or image recognition, that is a sort of solved problem for everybody. So nobody's talking about this anymore. So everybody deeply believe that it's going to be done, and this is basically done by deep neural network. So it was 2015, as we can see. So that was the twist point where proposing neural networks given the computers, so you can just train it on your computer, and they could do better than human beings. So if I show you images of cat and dog, then at some point you're going to do mistakes because those images are not perfect, but those machines can do less mistakes than you. And this was somehow inspiring. Another thing is ChatGPT, which is a sort what we call it a language model. So it had been a kind of dream for human beings that would just make a machine a computer which can react rationally to what we say. So I say, how are you doing? And then it just answer something meaningful. And again, there have been lots of trials for that. And many people try different approaches. And it could do it to some extent, but at some point it just failed because all of them were based on some predefined analytics and rules. But then the idea of using deep neural networks came across, so the idea of natural language processing got developed after the deep neural networks got somehow established in the literature, and then nowadays you have this ChatGPT, which you can ask, simple questions like what I said here, and then you get a total page of meaningful responses, which are not only coherent, but they even add to your information. So that was one of the great things, which we hopefully get to know in this lecture, how they work. And the other thing is the idea of playing games. So playing games, again, was one of the initial things people wanted to do with computers. So can we train a computer? Can we write an algorithm that could play with us chess? Chess, the hardest game we could think of, or the game Go. And then this was a question, and people since 1951, Turing actually developed a machine or wrote down an algorithm, which he wasn't trying to just do that. And for a long time, people again came up with this idea that, it's at the end of the day computation, and we are, whatever we do, we are limited in computation, so we are not going to beat human brain. But then again, the idea of neural networks came into account. I mean, the very, very first one was not really a complete neural network, but gradually it somehow got the flavor of neural network. So, anyone knows Garry Kasparov? No? Everyone knows him? So Garry Kasparov is like unbeatable chess player. In 1989, you played with IBM. So IBM started to think of writing down an algorithm based on this machine learning. So we trained something to play instead of just doing the full complexity search. And then the first idea was deep thought, which was somehow a combination of, deep search plus some training of models, simple models back to them because we were limited in computation. And then IBM developed this guy and wanted to just beat Garry Kasparov. So 1989, first try, they couldn't. So Kasparov happy went back home. So 1996, they called him again. He went there, he beat it again, the Deep Blue, the new machine. So he was again happy. But this happiness was only 1 year because in 1997, the Deep Blue one, after getting improved, could be Kasparov. So check YouTube, you're going to see that, very emotional moment when Kasparov is just standing up and feeling like he finally lost to a machine. So, and from then, people started again to believe that this deep learning or neural network could do something within this chess playing or this game playing area. And they started to develop ideas over and over. And the last time anyone could beat the computer was 2005. And after that, nobody up to this point could beat any computer. And you might have heard of AlphaZero, which was developed by DeepMind. And then the idea is to just train a neural network, which could be trained with a simple computer within 24 hours. And after 24 hours playing a game, it's going to play with the world champion and going to beat it, which is very impressive. So you can train a machine within the course of 1 day to be better than the grandmaster of chess. And there are still new things coming up, and all of them are done basically based on deep learning. So deep neural network is the key components also there. And this one, we are not going to cover it because this is the topic of another course, the reinforcement learning course. But I mean, if you want to do that in a reinforcement learning course, you really need to know what deep learning is. So you need to be able to train a neural network if you want to implement AlphaZero at the very end of the day. So Another topic is the translation. So, again, I'm not sure if anyone could remember, but somewhere around 2010, 2012, if you use Google Translate, it was not doing very well. So there was jokes like, yeah, so somebody takes some banner in different language, and then you could simply find out that it was translated by Google. So they couldn't speak that language, they just write it down in Google Translate, then it just translate word by word, and maybe do simple permutations, and then you have it. But it's obviously not the correct translation. So there was some idea that was developed at that period of time. It was called statistical machine translation. I mean, it was not like totally off, because this was the point where translation based on autoencoders came, or language models came to play, but they were not that successful. And then deep learning or neural machine for translation, they started to kick in, and they could do a great job. Okay, so it started with this Baidu company in 2015, then like DeepL, deep language company, came out, and then gradually, like Google even started to use those neural networks. And nowadays, you can pretty much talk to DeepL and then translate for you, and it most of the time does a better job than even a native speaker in both languages. Now, so again, that one was done by neural networks, and we are going to get a bit of this at the very end of the semester. So when we start to talk about statistic models, we're going to just design one simple language model, one basic language model, where you get the idea how we can do it the way that the other things would not do it. Okay? So, and these are all things that have been done by deep learning, so I hope that I could motivate you that it's good to know what deep learning is. But now let's get into the serious part. And then the question is, these are all nice examples of deep learning, but what exactly deep learning is? So deep learning is a subset of machine learning, which uses deep neural networks to execute a learning task. Now, you see me just underline some words here for you, which are the words which you need to know in this chapter. So basically, you might tell me, okay, we don't get anything from that sentence, okay? The only thing that might be obvious here is that, or might be understandable here, is that machine learning is something that includes deep learning. And then in deep learning, we're using neural networks and the deep version of them, and we're doing some learning tasks. But what are these things? And then this is the whole purpose of this chapter. So I want to tell you what the machine learning in general is, and then what are neural networks, why we use them, so you can see that they are special case or example of models you could consider in machine learning, and then when do we call them deep, and then you're going to understand what the learning task is and how we can execute that. Okay, so we basically learn this stuff in this chapter. For that, you do need a bit of background on optimization, linear algebra, things like that, which I give you here. Okay, and this is the whole purpose of this chapter. And then let's start with the chapter. Before I start, any particular question? I think it was just blah blah, but yeah.
I'm curious, just because, so for the for Alpha Zero, for instance, or for D4 or D2, would I be able to pass the competition product after the time that was?
For Alpha Zero, yes, because Alpha Zero is not that old.
What about D12?
I mean, they were not complete like deep neural networks. So initially, they were always thinking of like exhaustive search, and then they do it on the tree, and they do it very efficiently. So while bigger the algorithm, they would basically do that, but with the most efficiency. But in order to learn like the policy, they're going to put some simple model. That one was a deep neural network. And then when we talk about deep neural network, as you're going to see, it's not, you don't need to really have 10 layers. I mean, even 2 layers is still called deep neural network. But back to then, like they leave it trending for months. But AlphaZero was the first one which could do it in days. So, any questions? Okay, so then let's start with the machine learning. So the first thing that we're gonna talk about is machine learning. And I've copied this part of the Goodfellow textbook. So what the machine learning is a form of applied statistics with increased emphasis on the use of computers to statistically estimate complicated functions. So I don't know you, I guess you're all smart enough to get what he says, but if I were you, I would get it. So it's a quiet, like, tough explanation. So let's do it my way, okay, the stupid way, my way. So that is that there are, when you deal with any problem in practice, okay, there are two different kinds of approaches that you can do. The first one is the analytic one. And people used to believe that analytic one is the best one because you have foundation, you have something concrete, you can rely on it. That's to some extent right, but you cannot do it always that way. And the second way that you can do is to do data-driven way. And data-driven way means that you don't have access to like analytic rules, you don't know the physics, the philosophy behind the thing. You just start watching things, and then you develop some mathematical or statistical model that's gonna predict what's gonna happen next. Yeah, and this is the way that we do the data-driven analysis, or we develop data-driven algorithms. So why do we need data-driven algorithms? Because sometimes we don't know the physics behind the story. Either we don't know it really, so nobody knows it, or we do know it, but it's too complicated to be checked, okay? And to give you a very nice understanding of that, let's go for a very dumb example. So what is this example? We get this projectile, say, a ball we have, and I put this ball somewhere here on the table. And what I'm going to do, I'm going to initiate it with speed v. So the velocity v in this direction is going to initiate the ball. What's going to happen to the ball? The ball is going to just move and then hit the ground at some point, right? So simple physics, yeah? So I'm showing now the y-axis. So this is the height from the ground. The x-axis is this axis. And then I put the projectile here at the height h, and then I'm going to initiate it with velocity v. Okay, so I'm going to initiate it with velocity v. It's going to move, and then it gets down. It hits the ground at some point d from the table. Okay. Now what I want to do, I want to calculate this distance. I don't want to calculate it for one particular h and v. I want to calculate it for any h and any v, meaning that you tell me what is the height and what is the velocity, and then I tell you where it can hit the ground. And I am 100% sure that all of you have done it at some point in your high school or maybe in your undergrad general physics. You do all know it, but let's do it once together. That way, which was the analytic way you got used to in those lectures. So the problem is clear, yeah? You know what we are going to do. So I give you the height, I give you the velocity, and I want you to tell me what the distance is. And how do we do it? I mean, probably all of you remember. If you don't remember, I mean, don't panic. I mean, I just cheated. I just checked Google before I write this down first time. Okay. So I also don't remember what I did undergrad. So what we have a projectile, and then if you know the velocity v, then at every single time starting from the initial time 0, time t, you can say x, the distance, is v times t, because it's just moving with constant velocity in that direction. And for the y-axis, the vertical axis, it's gonna just get down because you have gravity acceleration. You're gonna get into, change the vertical axis with this equation. So g half t squared, this is the direction that it goes down, and then plus h, which is the initial height, yeah? So if you don't remember it from high school, totally fine. And just take it from me, okay? Clear? So if I want to just find out what is the distance that this ball is going to hit the ground, what I'm gonna do, I'm gonna first say that, okay, if I want to hit the ground, then I need my y, which is my vertical distance. I want this guy to get 0 because I want to hit the ground, yeah? So I'm gonna put y to be 0. If you put that guy to be 0, then you can solve this for t, and then you find this t0. T0 is the moment that you hit the ground, yeah? That t0 is simply put y equal by 0 there. So it's gonna be g half t0 squared equal by h, and then you solve it for t. It's gonna be t0, yeah? And then you replace this t0. So I'm gonna write this t0 to be 2 over g. G is the gravity acceleration, so it's gonna be something around 10. So I have this gamma, which is this square root of 2 over g, some fixed number, and then t0 is going to be gamma square root of h. I have that guy. I'm going to put t0 into the equation for x here, and then I'm going to get x equal by d, because at the moment that I hit the ground, my x, my distance from the table, is actually that distance d that I was looking for, yeah? And this d is gamma square root of h times d. So I just replace t with t0, and then that's going to be the distance, yeah? Now, if I tell you, if you get this equation, this particular equation, d equal by gamma v square root of h, if I give you any h and any d, then you're going to tell me what the distance is, yeah? So you have written a function. This function can get the inputs, which are the height and the velocity, and then it can give you back the distance where you hit the ground. Yeah, the output is the distance you hit the ground. Clear, yes? So that is something that you used to, and this is what we call an analytic approach to solve the problem. What do you need here? Even though it's a very basic problem, we have done some assumptions. The first thing is that we believe on Newton's law. Yeah, we believe that it's right, at least the speed and distances that we are working with, they are fine, working, and we found it out of experiment actually. But anyways, we believe on Newton's law. This is the first thing. The second thing is that it was given to us. So somebody or teachers at high school just told us those Newton laws. Yeah. The other thing is that solving the problem was too easy here. Yeah. So for example, here, when I wanted to find t0, I had to solve this equation. But this equation was very easy. Yeah. But what if I end up with a very complicated equation? Yeah, I might be unable to do that. Yeah. So two important factors. The first one is the laws of motion. So things, the analytics behind the problem that I do know them. And the second thing is that I could do it computationally. Yeah, I had enough computation power to do this. But it might be that I have sort of problem where I don't know the physics of it, or I do know it, but it's too complicated to solve the equations. And just to give you an example, for example, just think of a glass of water. And for all the particles within that glass of water, which you can think of, the number you cannot even imagine how many particles they are, you can write down motion laws, yeah? Then you can find out what is the speed of every single particle inside this glass of water. But you can never ever imagine a computer which can solve that system of equations. So even for that very simple problem, you cannot do it. Yeah? There are lots of other problems which you and I, all of us know, that we cannot do it, even though we do know what is the physics. And still there are things that we don't know the physics. Yeah? One simple example. What is this exact function which gets an image of a dog and tells us what kind of creature that is. You can write it down as a function. We're gonna see it. Okay? Well, what is that function? No one knows, yeah? Maybe there's no function at all, yeah? I mean, it cannot be no function at all. I mean, at the end of the day, there exists one function like that. But who can say it? No one. So it might be that you don't have the physics, or it's computationally feasible for you to solve that. And then what you're gonna do, you're gonna do a bunch of experiments, you collect some data, and then looking at that data, you start to develop one algorithm, which gives you some approximation of how you can do this. Okay, now, let's just focus on this very stupid example, and then do the machine learning or data-driven approach for this one. And hopefully by that point, you get the idea of what I do mean by data-driven approach. But any question before I start? No question? Cool. So if you got no question, then let's do it that way. So now I am someone coming from like Stone Ages, and I don't know the physics laws. Okay, so I don't know motion laws, and I want to just use data driven. So 1,000 years ago, this still existed computers, but no motion laws. So what I'm gonna do, I'm gonna put the ball here at one specific height and initiate with one speed, and I hit the ground. Okay. I get one distance. I do it at another height. So I put it another height, and I initiate it with another speed. And then I check where it hits the ground. And I keep on doing it, say for 1,000 times. Yeah? So I collect 1,000 data samples. Each of these data samples, each of these data points, contain one input, and that input is the height and the velocity. And also gives me one output of that function, which I don't know. And that output is the distance where I hit the ground. Yeah? I can do it by experiment. So I get the meter, and I get the speed meter, and then I check all of it. Yeah? I do as much experiments as I can do. So say I have collected different examples. So now what I do have, I have a bunch of data points which are collecting those v and h, and also I have the output of the function in those data points which are the distance in I. Okay. Now these are samples that I collected about this data. And now what I'm going to do the next, I'm going to assume that this v is related to those inputs with some model, with some function. But I parameterize those that function. So what does that mean exactly? So let's do it together here. So I just assume a kind of predefined function. So I say that I assume any of those data points, so d and h, is related to d in this form. Yeah? So there exists one weight W0. I don't know what it is, so I leave it open for now. There exists one weight W1. Again, I don't know what it is. I leave it open for now. So I have these two weights, and I assume, pay attention, I'm assuming that D is related to V and H with this model. So is it a right assumption? Is it? No, yeah? We have seen it. I mean, it's not the analogy solution. I mean, if you believe on Newton, then this is not the case. I mean, this is the exact relation, yeah? But I don't know that, so I'm going to assume something, yeah? And I have two things, W0 and W1, which I keep them general. So I keep them open to be designed, to be selected, to be chosen, right? Now, I'm going to say that, okay, this is the relation that I have between distance d, velocity v, and height h. And now what I'm going to do, I try my best to play with those two values, W0 and W1, so that, at least on the experiments that I have done, on those data that I have collected, I see that this di being W0, V0, Vi plus W1 Hi, this is happening. So I try my best to fit this model, into the experiments that I have collected about this, HV, the height, velocity, and the distance. Okay? Clear what I want to do? So W0, W1 are general. I have not selected them. I want to find the best choice for them. Yeah? So that my data collection is very well fit. Okay, great. Now, if I want to just match this predefined function to my data, what I'm going to do, I am going to do it like that. So I'm going to say, okay, for every single I, what I want to happen, I want di, this is the distance that I collected with the experiment, to be exactly that W0 star, so this is the choice which I like, okay? W0 star times the collected velocity plus W1 star, again, the choice that I do like, times collected height. Okay, I want this to happen for every single I in my data set. Right? And what can I say instead of that? I could say, okay, if I calculate the subtraction or difference between this D and this guy, I want this subtraction to be, this difference to be exactly 0. If that is 0, then it is square, the squared is also 0. Yeah? So I want this to happen. Yeah? And when I just write down equal with that, sign on top of it, it means that I want this to happen. It doesn't necessarily happen. Okay? I just want it to happen. Clear? What I want to do? So I want to find those W0 star and W1 star so that this thing happens for every single I, every single data point that I've collected. And if I want this to happen, I can, instead of that, if you're unclear, write it down in this form. So I can say that, okay, every single guy here, I mean, it is a square term, yeah? And every single of that is positive, right? So if I sum them up, if I add them up, it's gonna be 0 only if every single guy is 0. Yeah, right? So I want the summation to be exactly 0. I want it to happen. When this happens, this means that for every single data point I collected, that relation is holding. Then I have the right choice of W0 and W1. I want this to happen. But now one question. If I have, say, for example, 1,000 samples of data, do you think that I can make it exactly 0? Do you think that it's going to happen? No.
No. You have two features that you're looking at. And there's comparing on to the axis, you don't have to form a linear relationship.
Exactly. Exactly. So you cannot do it because you do know that this equation is not exact. Yeah? And then if you want this to happen, then what you want to, you are just collecting like 1,000 equations and only two variables to design. Yeah? And then one of those equations is going to contradict the other. Yeah, definitely. They only do not contradict if the model was totally right. Yeah, so as your friend said, this is not going to happen. I mean, you can get a bit of more intuition into it after you do the assignment 1. So I'm just giving you some spoil here, but you're going to see that if the number of samples is more than 3 simply, then this equation, this thing is not going to happen. This is not going to be exactly 0. Okay? Now, taking from my size cannot be 0 if I collect too many data points. Then what can I do then instead? I approximate it. What is the best approximation of that for you? What choice of W0 and W1 you would choose in that case, if you cannot do this? I would rather minimize this guy, this summation. Yeah, I'm going to minimize it in terms of W0 and W1. Because I would say it's not going to be 0. I want it to be 0. This is something non-zero. So the best thing that I can approximate what I wish is to just find those W0 and W1, which make the summation as small as possible. Clear? Everybody got the idea? So I guess many of you had this before when you were doing undergrad labs, at least the squares method. This is basically the same thing, yeah? You're exactly doing least squares method with a linear model, okay? Now, how can I find these two guys? Basically what I can say, I just make it as small as possible because I wanted it, I wish this is 0, I cannot do it, so I just try to make it small enough, yeah? And how can I do this? I can just write down an optimization problem. So I look at this whole summation as a kind of a function in terms of those two weights, which I kept them open, so W0 and W1. And now this function, I can optimize it in terms of W0 and W1, meaning that I go ahead and solve this minimization problem. So I minimize that term, that L term, in terms of W0 and W1. So I find W0 and W1, which minimizes this summation. Okay? Clear?
Yeah, so here we took the square, but I wonder why didn't we take, for example, the absolute value or
You could do that. So that is a choice again. Yeah?
do we get the same answer?
Not necessarily. No. And then the question is which one is the best? And then the more important question is what do you mean by this? So everything gets like deeper and deeper. So yeah, but we're gonna discuss it. This is a very valid question. So it's a choice of loss function that's that. Okay. Any other question? So everybody's clear about what we did here. So we did a no physics law. We just collected some samples. We considered a linear model, a linear relation between velocity and height with the distance d, and then we just try to find the best linear model that does it for us. And to do that, we just made this summation, and then we just try to minimize it, yeah? Because this is the best we could do. Clear? Now, what we are doing here is basically we're just minimizing the empirical risk, or we are actually minimizing the loss in this problem. So you're going to see it very quickly. I mean, by the end of the week, hopefully. So this thing here, as your friend validly mentioned, so this is a choice of loss. So I have chosen to just write the loss in this form. I can choose different losses. That's fine. We're going to see it for any specific task, any specific problem that we have. Out of experiments, we do know what is the preferred loss function, but this is again a choice. But what I have done in this approach was the data-driven solution to the original problem, which I could solve it, this particular problem, I could solve it by analogy approach. But this is an alternative approach. And for this one, this makes sense because the problem is too easy. But for many other problems, this totally makes sense because there is no analytic solution or it's infeasible. Here? So now, what we have done here, so this is the ML approach. And what you're going to get out of this ML approach, you're going to get a model. So your model is basically those W0 and W1. That's it. That is your model. No? You're going to get it and you're going to train it, meaning that you are going to find those star version of them, the best choice based on the loss that you have defined. Yeah? And then you're going to get this and you treat this linear model as the kind of function that relates HV to D. Okay? You're going to take it. But there is one difference here. I mean, in the analytic approach, you didn't need to do any sampling, any data collection. And as long as you believe on the notion laws, you are going to end up, it doesn't matter how you solve it, you're going to end up with the exact function. But in this case, you could end up with different solutions. And it depends on many things. For example, if I change the number of data samples that I am collecting, I am going to get different solutions for W0 star and W1 star. And my model is gradually getting better and better. Yeah? This is a difference because I just assumed a model. And the best I can fit it is to collect more and more data. So this is why we call this approach the data-driven approach. And for this particular example, you're going to program it on in the first assignment, and then you're gonna see that when you increase I, they gradually go to fit the true function. I mean, it's not going to exactly match it, but it's going to approximate with less error. Okay? So everybody's clear? Any question? Yeah, I need to have more than half an hour of lecture to just convince you to ask questions, so yeah. Yep.
Pretty much you are saying like with a large number of data, you are getting accurate model, but you're assuming that your data are valid and that they are real life. But it happens what we have, but it seems like really layered.
Then we're gonna discuss it. So for the moment, you're right, and this is a valid comment. So I believe that I do very accurate measurements. That's so they're right. No? But if that happens, then I need to handle that, and that is a part of lecture as well. So how to clean the data, how you can test whether your data is trustful or not. That is not. No. Any other question? Yeah. Yeah.
And this is a first lecture, so
Sure.
might not. So do you think like this machine learning data approach is considered as
Pseudoscience. If I want to be good with myself, no. Many people consider it like pseudoscience. I mean, it depends how you look at it, yeah. So I guess those who call it pseudoscience, they either don't really have the feeling about what the purpose of science is, or they don't know what machine learning is. So I wouldn't say this is totally pseudoscience, because we do know that we're doing this sort of approximation or just training something based on creating things. Yeah? So no, I wouldn't call it pseudoscience. But the key point is that you do know that it's not a magic. So you are not doing, I mean, gradually when you get trained on the topic of machine learning, you do understand that many things that you hear in the news are totally nonsense. No? Things like what happens if the machines are going to control the earth? That is never going to happen. No? Things like that. So, I mean, I wouldn't call it pseudoscience, but it's a kind of engineering science. It's not a, say, abstract science. Definitely. No, it's not. Actually, this is the purpose of this course. So I'm going to teach you that this is not a black box. I'm going to show you. You're going to see it, and then you'll laugh at those people who call it like some miracle. It's not. It's basically what I did here in a large dimension. And why it works, because when you make everything very large, it's going to work. That's the only reason. No? So you're going to see it. Don't worry about that. But no, it's not a kind of black box. Pretty sure. So you're gonna be upset when I insist on too much detail. Okay. Any other question? By the way, they're a good question. I mean, you could ask lots of people questions, challenge people. Okay. So now, if you got the idea of this example, this is a very simple example of model or data-driven approach, or say in general, machine learning algorithm developed for solving that particular problem. And in this problem, we had three main components. The first component was the data set. So when I wanted to start using this approach, I started to do experiments. Yeah? I collected heights and velocities and the distance, and collected too many of them. Because if I didn't have those data samples, I couldn't do anything. Yeah. So I needed some samples to train my model. Yeah. So this is the first thing that we do need in any data-driven approach, data set. The second thing is the model. And what is the model? Basically, what we assume, the predefined function. So I assume that D is related to V and H in this linear form. And I left W0 and W1 open to be designed. And that was the model that I consider for this problem. So, is there any reason that I consider this one? No, simply because it was too simple. So you might come up with another model, You might do know what is the exact model, you do know exactly what you solve the Newton's motion law, and then you know how they are related, so you put that one as the model. That's fine, Okay? But this is the kind of assumption that I did. This is what we call it model. Neural networks are spatial kind of model, So you just assume that the input and output are related with that neural network, which you are going to see what it is exactly in the next chapters. Okay? And the last thing was the loss. I decided to just calculate the loss, or when I wanted to minimize or find those W0 and W1, the optimal for, I decided to just minimize this guy. As your friend said, you could just come up with another metric to calculate the difference, And nobody can claim that that metric is bad or good, right? So this is again the third thing that you have in your machine learning approach, the loss. So three things, always we're going to have it in any machine learning problem. And they are the key components in deep learning as well. Okay, so these are the main components. Now, the story is over on this sample, the simple example, and I want to start with a more serious thing, where we just start to just understand these components one by one. But before I do that, any question on that?
Just going back to picking out the loss function.
Yes.
Do we want to, I guess, when we do pick up the loss function, like for example, this one, we know if it's a good or not. The same, it's an easy loss function to calculate just because it's differentiable. Do we try to pick a loss function that's more differentiable versus not, or?
Yeah, we're going to see it now. Once you do know how to do the optimization, I mean, if you want to do the optimization, definitely prefer some loss, which is differentiable. That is what they're right. And it's not the only thing. Sometimes you want your loss to just penalize those weights in the model in a way that you desire. We're going to see them as well. So for a simple classification problem, you can use this square loss, which is the mean square error, or you could use, say, cross entropy. But we always use cross entropy. Why? Because that one penalizes everything much more strict. Okay, so we're going to see that, but there are a bunch of reasons that you choose one, but at the end of the day, you can only give a bunch. So it justifies. It's your choice. Like you want.
Must be differential, but.
We're going to see it. So maybe for back propagation, definitely, but we're going to see it. We're going to see it a lot. Okay? Yeah, but that's right. You definitely need, because you want to solve the optimization problem. So, yeah.
How does their models to loss functions?
Yeah, when we test the model. Okay, so if you have, it's the problem of validation. So if I choose two different loss functions, then I can do the training once with one, and do the training again with another, and I get two different models. Then I can get those models, and then I can test them. So I collect new data, which was not in my training data sets, and I test it. And I just compare the results, see in which one I get more error. And then again, what do I mean by more error? Then you need to define it. Sometimes it's easy to define it, like it's a classification problem, so you really want it to work, Sometimes it's hard, like the regression problems. So again, it comes back to your preference. Any other question? So if you got no questions, then let's do some review on some basics, which, I mean, they are very basic, but I just want to give you the notation. So you do understand what is the notation we're going to use. So the first thing is the notation for vectors. So a vector is a one-dimensional array, and then we collect all those numbers in this array. And then when I write it down like x is within the real axis r to the power n, I simply mean that I have a vector with n different components. And all of them are real value. They are real numbers. And when I say vector, you immediately think of a column vector. If I want to make it a row vector, then I'm gonna put the transpose on top of the vector, okay? Not everybody use the same notation, just to be clear, this is how we do it, to just make the amount of confusion minimum in the course, okay? Now, this is the row vector, this is the column vector, and then notationally, most of the time, almost always in this lecture, I'm gonna show a vector with a small letter boldface, just to make it different from the matrices or tensors, okay? So, that's it, and as I said, a vector by default is a column vector. If I want to make it a row vector, I simply transpose it. This is the first thing. The second thing is a matrix. So a matrix is a two-array collection of numbers. Again, I'm going to say R to power n times m. N is the number of rows that I have. M is the number of columns that I have. And we can always look at a matrix as a collection of vectors, right? So one way that I can do it, I can say I have 10 columns, yeah? So I have n different vectors, and each of them is of dimension n, yeah? So each of them is of dimension n. These are column vectors next to each other. One way of looking at it. Another way is that I can think of n different row vectors stacked on top of each other, and each of them is of dimension n, yeah? Okay, so I can look at it this way or that way. No, that's fine. And sometimes one of these ways is easier to use. Okay. Now, when I want to refer to a matrix, I'm going to use boldface letter again, and this is going to be capital. So like here, capital A boldface. Now, just again to distinguish it with vectors. And at some point, you're gonna just ignore it because that is too easy, too obvious for you. But just for this start one. And the next thing is that what if I want to just multiply two vectors? Yeah. So I could do the inner product. If I do the inner product, I get two vectors, and then I get as the product one number. Okay. I'm going to write it down in this way. So I can say X transpose. So first the row vector, then the column vector next to it. They get in a product. That simply it means that I get every element, every corresponding element, multiply them, and then I sum them up. Yeah? And then this is what I call it the inner product. Okay? It doesn't matter if I have X and Y. It doesn't matter if I inner product X to Y or Y to X. They're both the same thing. They're going to end up with the same value. Yeah? I do have also the outer product. The outer product is getting two vectors, for example, and then it's going to give me a matrix. Right? So if you want to look at or consider this one, or even visualize this one, like you have X, so you have X1, for example, X2, Xn. And then you multiply it to this other row vector. So you have the X vector itself, and here you have the transpose, the row version of it. So it's going to be Y1, Y2 to Yn. So it doesn't need to be for outer product. They do not need to be of the same dimension, of course, but just here for this particular example. So then you're going to say X1 times Y1 is going to be here, yeah? X1 times Y1. Then X1 is going to get multiplied with Y2, so here is X1, Y2, and so on. You keep on going, right? So this is the outer product, and obviously, I mean, if you outer product X to Y, it's different from outer product in Y to X, and that shouldn't be a transpose here, I guess. So it should be YX transpose. Sorry, so the title, you see. So. But if I get X and multiply it with outer product to Y, it's going to be the transpose version of outer product of Y to X. No? Not so challenging, just to keep you up like into the mood of the calculations here. And you can extend everything to the matrix form, of course. Like, for example, if I want to get one matrix A and multiply it to one vector X, I can think of, for example, this collection, so I can think of it to be a collection of column vectors. And then you can always imagine this by considering the dimensions, of course. So what you can say, so this is a kind of one. So this is a kind of useful thing you can keep in mind when you're following the calculations on the board. So one way that you can think of it always is that you can say, I have matrix A, and this matrix A is of this form, so it is A1, A2, so on till AM. So you have M different columns. These are all vectors, yeah? And then you multiply it with X, which is X1, X2 till XM. And what does that mean? You can say that I get this guy, I multiply it with this vector, and then add it up to this guy being multiplied to this one, and so on. So you can write it down as X1, this is a number, times vector A1, the first column vector, plus X2 times A2, and so on, yeah? So this is one way of looking at it. This is sometimes useful, but the other way is the classical way when you do the calculation, yeah? So you can think of it as the collection of row vectors, and then you would say, after multiplying to X, I basically get every row vector, and then inner product is with that X, which is giving me that vector at the output. Same thing then. Clear? Any questions? No question, okay? So, if you got no question, just have the notation. So I'm not going to do any calculation right now for you. Now, let's start with the first component. So I think I have a couple of minutes left, and as I'm not going to lose any minutes, so I am going to keep on with this guy. Okay, I don't know why this is not, okay. Yeah, I have still 10 minutes. So let's start with the data set. Let's define data set formally. So we have for our dummy example, our data set looked like this one. So I had a data point, and that data point consists of two things. One input to the function that I try to find out what it is, and that input in my example was the velocity and height h, v and h. The other one is the output of that function, d. This is what is going to be returned by that function, right? And I can always write it down in the form of a tuple. So when I get my data set, I'm just collecting I of these tuples. No? So a tuple, I simply mean I have an input and one output, yeah, in each tuple, and I put them next to each other, right? Okay, so a data set is a collection of those data points, and what we do have here is what we call it the label data set. Why? Because once I fix the input, I do the experiment, I calculate the output. So I'm gonna say for that input, the output is this guy. So I am labeling every single data point. This is what we call it label data set. And if I want to write it down in general form, then it's gonna look like this. Yeah? So I have a tuple, and this tuple consists of two things. One input, which is potentially a vector. So I'm going to show it with xi. One output, which is again potentially a vector, but most of the time we're thinking of it like, because we're mostly playing with the classification in the first parts of the course, then we can think of it to be a simple number. Okay? Now, this x is the input to the function that we don't know what it is, and we want to just find it out. And that y is the output of that function once it has been excited with that input xi. Now, and we call that y to be the label of x. So we label that input with this output. Now, you might come up with this. First of all, if I had a labeled data set, my task is very obvious in the problem. So what is it? I have the input, I have the output, and then what I need to do, I need to just find out what is the function between this input and output. And how can I do it? I just specify the model, I specify the loss, and then I find every element in that model by minimizing that loss. Yeah, this was what we did in our dummy example. Yeah. In that case, the learning problem, which is basically to find out those weights inside my model, is obvious. And this is what we call it the supervised learning. So here, the learning task is to simply understand the relation between the input and output. And as I said, it's a kind of supervised learning problem. Why it is supervised? Because we think that there exists a supervisor. It's just telling us, giving us some data, or we're just looking at a bunch of data, and it's telling us what is the label, the corresponding output for each data. Yeah? So x1, it says, okay, the output is going to be y1. x2 is going to be y2, and so on. So it fills you with the labels in the data set. This is the supervised data set. And when you have a supervised data set, the whole task is supervised learning, meaning that you want to know the function. And what we do in this lecture, say 85% of the time is supervised learning. You might wonder, is there anything called unsupervised learning, or can we have a data set without labels? And the answer is for sure. I mean, there is also unsupervised learning, and in unsupervised learning, you are simply left with a bunch of data. So you have those x's, you don't have any y. What do you want to learn then? Yeah, that is a very massive question. And you're going to see that depending on the purpose that you have, you can make up some sort of labels for yourself. Okay? That is the kind of problem which we call it unsupervised learning. So your data set only has the data points, it doesn't have any label. And then what you want to do, you want to find out a kind of feature, a kind of property in this data. And nobody's telling you what exactly you should look for. So you might guess that it is a more challenging problem, and you are right. But once you do know what it is, how you do the supervised learning, and you know what you are looking for, then you can convert that unsupervised learning into sort of supervised learning and solve it. Okay? So what we're going to do in this lecture, we are going, as I said, for the 85% of the first part, we are just going to deal with supervised learning. And at some point, I'm going to tell you, okay, let's just look at this problem. And there you see that there is no label. And then you get this is an unsupervised learning problem. But at that point, you already do know how you can make a label for that. Yeah? And this is the tiny part of last part of the lecture where we deal with a bit of unsupervised learning. Okay? So I am going to discuss this particular example next time. So this is the example of PCA, principal component analysis. And after that, we are just going to get into the model and loss and training. Okay. Any questions you might have? Yeah.
Why is the label a scalar?
I am just assuming here for simplicity that is a scalar. It's not necessarily a scalar. It could be also a vector. It could be a bunch of data. But because for at least the first two chapters, we're mostly dealing with classification because this is the most straightforward way of, or most straightforward example. Then there it is always a scalar. Yeah, but it doesn't need to be. Yeah.
Aside from so in terms of supervised or self-supervised learning, aside from not being able to actually derive outputs, what would you say one is probably better than the other, aside from not being able to just derive the output?
Supervised versus unsupervised. Actually, it's not about being better or not. I mean, your problem by itself is either supervised or unsupervised. So if I give you the example on Thursday, you're going to see it. So it means that, I mean, you don't really have anything called label in that problem. But then you need to find out something. Yeah.
You're not measuring an output.
Yes, because basically there is no output. So like you went out, you collected a bunch of data, height, weight, I don't know, age of different people. And then you collect them in the data set. And now we want to say, okay, in this community, what kind of feature they have? No?
So it's more so a feature of the problem.
Yes, exactly. Exactly. Yeah.
Some people have supervised
Yeah, but Okay, you don't need to complicate things. Now, you could have semi-supervised, self-supervised learning, you can have things like that. But they are like more, say, narrow down terms. Okay? So, roughly speaking, supervised, unsupervised. For now, we just think of that. Okay? Any other question? Okay, so thanks, and hopefully I see you on Thursday.
We had a.